Hi everybody, how are you? We're going to go through a section here. I have been through your papers and I'm of the opinion that you would need to urgently revise the mole, and that can't be done without doing this entire section on masses, gases and moles. Now, can I start by saying to you that there will be accompanying notes with this, and I'd ask you please to have an A4 pad and pen and to write with me as we go through the section. Now, I'll do this in a number of modules and we will take breaks between them so that you can write them up. I'm starting then today with masses, okay, and we need to understand clearly what is relative atomic mass and what is relative molecular mass. Having that done, we will develop the idea of gases, which is quite a lengthy section, and having those done, it will then be possible for you to understand the concept of the mole. Now, what tends to happen in chemistry is background information is missing, and therefore a lot of sections lose marks. I'd ask you to go back and refresh yourself on this and make sure it's okay, and I think you'll be pleasantly surprised how well you're doing. Now, I'm starting then with the definition of relative atomic mass. And it would be very important for you to have a sense of that, okay, as to what it means. Now, I'm putting this on the screen for you, and I'd ask you just to be aware of how definitions are put together. This one tells you that relative atomic mass is effectively the mass of an atom of an element compared with or relative to an agreed unit. And like everything in life that we're going through, there is an agreed unit. And I'd like to think that you would work on that. The agreed unit I'm talking about in this case is a figure which is 1/12 of the carbon-12 isotope. I don't think you'll ever understand this if we don't do something with isotopes firstly. And I'd ask you just to be aware of that, okay? So I'm just going to check on my camera for a moment, excuse me. Right, that's fine. Now, let me remind you of isotopes. Isotopes are effectively atoms having the same atomic number, meaning they're the same element, but they have a different mass number because they have different numbers of neutrons in the nucleus. And it is important that you would recognize and go back to this particular concept before you go forward. If you look at a periodic table, you will pick up data that is meant to be relative atomic mass. And I'll just take a copy for you if I can and put it up there. Now, you obviously will be looking at your periodic table and you could look at anything there to give you an idea. There is carbon, and carbon has a relative atomic mass. Carbon equals, in this case, 12.01. That is an average value. So let me deal with that further. The common isotopes of carbon are carbon-12 and carbon-14. They both have an atomic number of 6. Are you okay with that? That means that this particular isotope has 6 protons and it has 6 neutrons. They're the number of protons, the atomic number. This is the mass number, protons and neutrons. Likewise here, this is 6 protons, and this is 8 neutrons. Now, there are more neutrons in that nucleus than there are in that. Now, I must check on something with you immediately. This is very important. Very often in Leaving Cert, they leave out those numbers. They leave out the atomic number, and it would be printed like that for isotopes. Will you be careful, please? Okay? If you look up carbon in the periodic table, it's always 6. I would suggest if this happens on an exam paper, write in the atomic number and there'll be no issue at all. Put the 6 in there and the 6 in there and you're fine. So there's the composition, 6 protons, 6 neutrons, 6 protons and 8 neutrons. They have exactly the same chemical properties because they have the same number of electrons, but one is heavier than the other. So if you were to take a sample of carbon, it would be made up primarily of those 2 isotopes. And you'd find that the relative atomic mass would be 12.01. In other words, that's an average figure. It would suggest, wouldn't it, that nearly all carbon is made up of that isotope and very little of that, because it's just over 12. it would predominantly be carbon-12. Now, that's the number printed on the periodic table, and we need to realize that, okay, that came from there. I'll come back to it in a moment, but I just need you to see, first of all, what we'll be doing with that. Now, next, have a look at that definition there and see how you're finding it, please. It's very, very important. Okay, this is the mass of an atom of an element compared with or relative to. Relative atomic mass. Relative to. Will you be careful with it, please? Okay, the word relative should not be used in the answer because you'll be accused of lifting it from the question. So be careful with that, please, okay? Compared to 1/12 of the mass of the carbon-12 isotope. The carbon-12 isotope has a mass of exactly 12, so 1/12 of it is exactly 1. You think that's okay? Because you need to be careful now that that's an idea. I hate to think now you'll be learning that as words. That's a concept, okay? And it's 1/12 of the carbon-12 isotope. Some of the texts expresses that in a different way. They would say on a scale where carbon-12 has a mass of 12. That's the same thing they're saying, but it's probably easier to recognize that. In other words, when you look up your periodic table then, and carbon happens to have a value of 12.01, that's an average value, and you must recognize the meaning of that. If we were talking about the average fifth-year class, and we were to say the average age was 17.1 years, what would it tell us? It would tell us that most people in the room were nearly 17, or one or two might be 18, but the average is 17.1. And that's exactly what that's telling you. And we have to be careful with that. The AR value, the relative atomic mass, capital A for atom and R for relative. The relative atomic mass, the value of that is given in the periodic table on page 79. And you'd always have that in front of you in the exam. So you could look that up anyway. But wait for it. In the Leaving Cert, that doesn't always happen in house exams now, but in the Leaving Cert, the actual values would be printed on the exam paper at the front. And they would write down carbon equals 12, sodium equals 23, or whatever. Okay, they'd be given to you. They're rounded off. The values are also given on the front of your exam paper, usually rounded off. Now, that's confusing. Be careful. Because rounding off is defeating the whole purpose of what we're trying to explain, the average or the mean. So be careful with that, please, when you're dealing with it. If you do, there'll be no issue at all. Now, I'm asking you to kind of recognize this, that you must have a clearly defined system. To make calculations easier, they give us these figures. If you have to go back to your formula table, I would be suggesting you'd round this off. And if you do that, you'll be fine. Now, are we okay with that? You think you have the drift of that so far? So there for the moment is how we're defining that. I'm going to give you a formal definition for this. That's a narrative or a description of what you're trying to say. This is the mass of an atom of an element compared with 1/12 of the mass of the carbon-12 isotope. So there's an agreed unit called 1/12 of the carbon-12 isotope. If you were talking to your friends about something you had purchased, for example, you had bought a top and you said you paid 23 for it. I think there would be an implied unit in that conversation. I think we'd probably assume that 23 meant 23 euros. On the other hand, supposing you were talking to somebody about the fact that you had bought a car for 23, I think the implied unit would be thousands of euros. So in this instance, I am saying to you that the idea of a unit here had to be agreed. And we imply it all the time. It's 1/12 of the carbon-12 isotope. The carbon-12 isotope has a mass of exactly 12, so 1/12 of it is exactly 1. And that's precisely what you'd be at there. Very good. I will be back on that because the formal definition is about to come shortly. Next, please take a look at this. Everybody has confusion here now. Distinguish between relative atomic mass, AR, and the mass number of an atom. Now, that begs the question always, whenever you're asked in Leaving Cert to distinguish between two things, where did you meet them? Out of what context did you take them? What chapter was it in? What part of the course was being examined? You met relative atomic mass right here under the section we're doing, which is the gases, masses and moles. You would have met mass number very early on under atomic structure. And there it is on the board for you already. There is a nuclear formula. That's what we call it, a nuclear formula. That there is called the atomic number, and that's called the mass number. That number is the number of protons in the nucleus. That number is the number of protons plus neutrons in the nucleus. So that's what the mass number is. The mass number is actually a whole number, right? You couldn't have 0.1 of a neutron. So that tells you the number of protons and neutrons in the nucleus, whereas this is an average of all the isotopes of that element in the sample you're talking about. And it's important that you're recognizing that. Now, please be careful with that. It's very, very important that you would know that. Now, we would need to look at the definition for that, which I'm going to put on the screen for you next. You'll be asked to define relative atomic mass. And you can't define this now without clearly making certain points in it. I have them there as bullet points. I hope you can see them now. I hope they're okay. As bullet points. You'll be asked to define relative atomic mass, AR. The relative atomic mass is, you must say the average mass or the mean mass. You must say that. You must say of all naturally occurring isotopes of that element. I've mentioned over here already the two most common isotopes of carbon are carbon 12 and carbon 14. I said that to you already. Okay, and as a result, the average came out to be 12.01. In other words, it's predominantly carbon 12, and there's very little carbon 14 in it. It says, taking their abundance into account, there's a huge abundance of that, and there's little of that, because the average is 12.01. And it's expressed on a scale where carbon 12 has a mass of 12, or if you prefer to say, compared with on a scale where 1/12 of the carbon 12 isotope is the unit. Okay, now it's important that you don't leave out any of those 4 points in the definition. If you do, you lose significant marks. It's not about you lose a quarter there, a quarter there, a quarter there. No, if you leave any one of them out, the definition is incorrect, so you'll only get a very small number of marks. So please be careful with that, won't you? That's a formal definition then, and we have to be aware of that, however we'll be doing that. Now, we'll look at calculations on it in a moment, but we need to bring it to a point first where we can use that. I'm going to deal next with relative molecular mass, if I can. The difference between relative atomic and relative molecular mass is simply that we're now dealing with molecules, okay? The relative molecular mass is MR, where M is the I'll put that on this side of the board for you so you can see what we're at, okay? Relative molecular mass, it is M for molecular and R is relative. And it's something similar now. We'll come back on the definition in a moment, but you need to see what you're trying to say first. This is the mass of a molecule of an element or compound. You must say of an element or compound. Okay, compared with or relative to, and here we go again, it's a repeat of that, 1/12 of the mass of the carbon 12 isotope. Now I'm going to go back for a moment. Why do we need to say element or compound? And the reason is because elements and compounds can exist as molecules. Most of our elements would have a molecular structure somewhere. Look at this. There is oxygen. It's a molecule. It's a gas. There's hydrogen. It's a molecule. There is chlorine. It's a molecule. Okay, and you could have many more. Nitrogen, let me put in there as well. They're all molecules, but they're elements. Compounds are all molecules. A compound is the chemical combination, all the C's, chemical combination, compound, of two or more elements, right? So here you go. H2O is water, okay, and you can work your way through that. H2SO4, write in your own favorite one and that, whatever one you want, no problem, okay, and you're dealing with them as you go along. There's carbon dioxide, right? They're all compounds. They're elements, they're compounds. And they're all molecules. So effectively, that's what you're dealing with. Okay, this is the mass of a molecule of an element or compound compared with or relative to 1/12 of the mass of the carbon 12 isotope. Now, you need to just keep in mind that, you know, when you're dealing with that, I've already mentioned to you about elements and compounds, but keep in mind, won't you, a molecule of an element has the same atoms, 2 H's, 2 oxygens, okay, 2 O's, 2 Cl's, or 2 N's. If it's an element, they will be homonuclear. They'll have just one type of nucleus, okay? Whereas if it's a compound, obviously, it has different atoms, okay? You have hydrogen and oxygen, you have hydrogen, sulfur and oxygen, and you have carbon and oxygen. And that's very important now. There's a concept now, please. From the beginning, I've said to you, the concept must be understood before you start defining it. And you need to go back and think about what you're saying. If you're remembering words, you lose it again very quickly, and it's very important that you'd be aware of that. Now, that's good. So I'm asking you the question then, can you define relative atomic mass? And can you define relative molecular mass? I'm going to put a formal version of that on the screen for you, and I'm hoping that that will make sense. Back again now quickly, let me just say to you what you're dealing with there is quite simple. I hope it's all right, okay? You're dealing with that one. You have that, okay? The relative atomic mass, the average mass, okay, of all naturally occurring isotopes, taking their abundance into account and expressing it on a scale that you've chosen. The scale that was chosen was that carbon-12 would have a mass of exactly 12. Or you could say 1/12 of the carbon-12 isotope to give you the unit. It's the same thing, but it's an agreed unit is very important. You can't leave out any one of them when you're defining it. The relative molecular mass is a little bit easier to work with. Let's look at that. A little bit easier to work with. You shouldn't have any issues there. Okay, take a look. This is the average mass of a molecule. Okay, you must say of an element or compound. Right, and it's expressed on the same scale. Okay, expressed on a scale where carbon-12 has a mass of 12 units. Right, and that's exactly what you want there more than anything else, and you need to have that. Now, the pieces I've underlined, they must be in your definition. And again, I'm saying to you, it's not 1/3 of the marks for each of them. If you leave any one of them out, the definition is incorrect. You lose substantial marks. If there was 6 for it, you might get 1. Now, please, it's very important that you're learning that as an idea and not as a piece of information. All right? Good. Now, how would that be examined then in terms of an exam question, and what would they be looking for? Let's look at how the calculation would work into that, and I think you'll find it very easy. I'm going to do this for a start out. Here's a question and an answer. Let's look at a question first and see how you'll find it, okay? And I will go through some of that with you now to give you a sense of what it's about, right? Chlorine consists of 75% of chlorine-35 and 25% of chlorine-37. What is the relative atomic mass of chlorine? Now, I will deal with the actual means of getting those percentages separately, but just how will you deal with that and what are you doing? Now, just attend to me a moment while I try and put this together for you, because it's most important that you have a sense of what you're doing here. Chlorine-35 is written there. We could write it like this. Chlorine-35. And chlorine-37, we could write it like this, because these are the mass numbers. Chlorine-35 and chlorine-37. Of course, if you go to a periodic table, you will see that chlorine is 17, so you could volunteer that anyway. I'm repeating again now, the 17s are not likely to appear on the exam paper. But I would make a suggestion to you. If that came up in the exam, on the question paper, I think I'd be audacious enough to read the question, look up chlorine in my periodic table, and put the 17 in there. That would be a good idea. That's the number of protons. That's the number of protons and neutrons. So the difference is the number of neutrons. So we would know the composition of them immediately. Can I just do that to make sure you're okay? That would have 17 protons, and it would have 18 neutrons, because I subtracted that from that. Okay, and that would have 17 protons, and it would have 20. Am I right? It would have 20 neutrons. Yeah, it would. Now, will you be careful at that place? Because it's most important that you realize what's happening here. Now, they are 2 isotopes of chlorine. They are 2 isotopes of chlorine. And there's a certain abundance. When you prepare a sample of chlorine, there's a certain amount of that with 37 and some of it with 35. And the relative atomic mass would give you the composition. I'm back again now to the analogy of the average age of a class. The average age doesn't tell you the age of any one individual. It tells you nothing more than what the approximate age of everybody is, and you have to work with that in mind, okay? Could I remind you about isotopes while we're talking about them? You could not distinguish chemically between the two of them. You couldn't do a test to say, oh, that's chlorine 37 or that one is chlorine 35. You couldn't do that. Why? Because they both have the same number of protons, therefore they have the same number of electrons. Let me digress for a moment. So there's your nucleus of chlorine, and it has 17 protons in it. So it will have 17 electrons on the outside. It'll have 2 in the first shell. It'll have 8 in the next shell. Does this sound familiar from a previous section? That's 8, that's 10, and it would have 7 in the last shell. 1, 2, 3, 4, double, double, double. And it has 1 single electron, so it would bond and has a valency of 1 and would do that. Now, whether you had that particular atom or that particular atom, it would have exactly the same number of electrons, form exactly the same number of bonds, so it would have exactly the same chemical properties. That's the thing about isotopes. They have the same chemical properties. You cannot distinguish between them chemically. And you need to be aware of that when you're working with that. Good. So I've made that point for you, and that's very important now. Now, they've told us here what is the relative atomic mass. Now, what they've done is they have given us the 2 isotopes. One is 25% and the other is 75%. That's 75%. And this is 25%. And basically, you are being asked to calculate the relative atomic mass of that, which is asking you, would you ever go away and calculate the average mass of that sample? So this sample of chlorine has 3/4 of it is that, and of course 1/4 is that. So you have to do that. And so the solution is coming up on the screen now. Take a look at what we do. I would call this the 100 atom method. I just made that up, by the way. Okay, the 100 atom. You work on the basis of 100 atoms. If you happen to have 75% of chlorine 35, then 75 atoms with a mass of 35 would have a total mass of this 2625. And if you had 25 atoms, 25%, with a mass of 37, the total would be 925. If you added them together, you'd have the mass of 100 atoms. And a simple division would give you the average mass of one atom. And it comes out as 35.5. So in that instance, that is your answer, 35.5. Now, if you went and looked at the periodic table, you would see that chlorine did not have that value. In fact, it's 35.45. And I wonder, why is it different? Okay, if you went and looked up the periodic table, chlorine has 35.45 printed underneath it. That's 17 on top, okay? Good. And that's printed on the periodic table. Why is it that? Why is it not 35.5? And the answer is simple. Somebody cooked those figures in the question. They rounded them off just to make your calculation easier. Are you okay with that? So the chances of something being exactly 3/4 and 1/4 in the sample are slim. And that's exactly what they're after here. Nothing more, nothing less than that. Is that okay? So I think it's very important that you recognize this, okay? 3/4 and 1/4. Okay, they were cooked, and consequently the number came out to be an exact figure of 35.5. Much likely to be something different to that. Now, that's what's in the periodic table. You'll be given that if you need it, but that's the calculation. Now, let's extend that a little bit, because I think there could be a problem here, and we want to be aware of this. There could be a problem with this, and we need to look at it. Now, I'm asking you to be aware of what's happening here so that you can deal with this appropriately. This is a different style of question, and we would need to look at it for a moment. I would prefer, if you were to pay main attention, that's the most likely version of the question. Here's a variation of it. Bromine, another element, consists of 2 isotopes, bromine 81 and bromine 79. And this time, just to make the point to you, sometimes the examiner writes the isotope that way, and sometimes the examiner writes the isotope this way. And that's very important, that you realize that that's the same thing. I'm reminding you again now, if you're asked this, it's likely the 35 will go missing, and the 35 will go missing here. So you'll be given bromine 81 and bromine 79. I've advised you already that you really should put in you'd look up the 35 in your periodic table, you'd see bromine is number 35, and you'd pop them in there just to remind yourself of that. So that one obviously contains 35 protons and subtract to get the number of neutrons. I think you have the idea in that, okay? If the relative atomic mass of bromine is 79.91, they've given you the relative atomic mass this time, and they're asking you the reverse question. What is the percentage of each isotope present? Now that's very important that you are dealing with that and dealing with it correctly. And so what is the percentage present? That's what you're going to deal with. And here's the type of solution we have to that. You have to start by making some statement along the lines of, let X percent be the first isotope. Therefore, subtract X from 100 and you have the percent of the second isotope. And let's work on the 100 atom method then to get this right. If you have X atoms at a mass of 81, then the total mass will be 81X. And if you have 10 minus X atoms at a mass of 79, it will be 100 minus X multiplied by 79. Okay, and therefore, if you added the two of them together, you get the total mass. There it is there, the total mass. And that's the mass of 100 atoms. And if you divide by 100, you're going to get, of course, the mass you want. So I've tidied that up for you. That's 81X, that's 97X, so that's 2X. Okay, so that's the mass of 100 atoms. And look where you are then, you're finished. Quite frankly, you're finished. The relative atomic mass is the mass of one atom. And you end up with that. That's easy enough. Put in the value they gave you, and the rest is a simple calculation. They gave you the relative atomic mass, so you must solve for X. I won't go there with you now. I mean, solving for X is something you do in your own time. That's it. And look what happens. You're going to get a value of X equal to 45.5. Okay? In your own way, in your own time, do that by your favorite method. X is 45.5. Put the X in there, and you can work out the relative atomic mass. Okay? Put that value in there, and your answer will come out to be, okay, 45.5 is the percent of 1. Put it in here, your X, and put the other one in there. Okay, and you have that. You could also work out various things along the way with that, but that's fine. 45.5 is the percentage of one isotope. Subtract that from 100, and you have the one of the second one. Is that all right? And that's effectively what we want there. I'm going to look at one exam question just to give a sense of how this would be examined. Now, I have to be careful with you here as I finish this unit that you're not getting confused. You need to go back and revise isotopes, way back there in atomic structure. Then you need to make sure you can define relative atomic mass and relative molecular mass. And finally, we have this piece here about calculations of relative atomic mass. You won't be doing calculations with relative molecular mass. You will not be doing that, so you don't have an issue with that. Just be ready for that. Let's look at just one question. Make a note of the year is all you have to do, and you can be dealing with it yourself in your own time. Okay? I'll take 2006. Please make a note of this. 2006, question 10A. 2006, question 10A. Right, just write that down and you can look it up in your own time as to what's actually involved in that. And there we go, there is the question. Now I'm sure that'll be difficult to read, but will you look it up please and you'll be able to work on it. What are isotopes? Okay, these are atoms having the same atomic number, meaning they belong to the same element, but having a different mass number because they have varying numbers of neutrons in the nucleus. Okay, we have that already. This one here, same atomic number, but different mass number. And the reason they have a different mass number, because that has 2 more neutrons than that one. And that's effectively what you're dealing with. Define relative atomic mass. Now I'm going to say no more to you, other than if you don't get those 4 points, the word average, okay, and going right through the one you've been presented with already, you'll be in trouble there with that. Be careful with it, please. You'll get very few marks if you leave any of them out. Be careful, okay? Allowing for the isotopes present, taking their abundance into account and expressing them on a suitable scale. If you leave any of those details out, you will not get those marks. You might get 1 out of 6. So please be careful that you are presenting an idea here. What is the scientific principle? They never use the word scientific, but always put it in when they use that word. What is the scientific principle on which the mass spectrometer is based? Okay, now to be fair to you, there are 6 instruments on our syllabus and they will be done at various stages throughout the year. And that's one that's done early on. You may not be familiar now, you may need to go back and look at that. The scientific principle is very simple, that they pass these charged isotopes through a magnetic field and the heavier particle bends less than the lighter one. Now I think you could probably appreciate that you know, if you were rolling 2 balls across the bench, and you try to blow them off the bench, the heavier one would be harder to move. And so they separate based on their masses. And the principle is that you can separate isotopes on their masses, based on their masses. That's what they want there, nothing more than that. And lastly, you're asked to calculate the relative atomic mass of a sample of lithium, given that the mass spectrometer shows it consists of that percent, 74%, and the remainder, of course, is 92.6%, okay? The isotopes are lithium-6 and lithium-7. Now, look at the way they're printed, be careful. They could well have told you that the lithium contains 7.4% of lithium-6, and they could have said, and the rest is the isotope lithium-7. In other words, you'd have to subtract that from 100 to get the second one. Now, there's a more modern way of presenting that data, and I'd need to bring that to your attention before we finish. Please apply that to the method I've just been discussing with you, and go and do that calculation now and see how you're working out with that. I think you'll be pleasantly surprised how well you would do with that. And the answer to that is 6.9. 6.9 is the relative atomic mass of lithium. 6.9. Are you okay with that? Do you need any help with that? I hope it's okay. Relative atomic mass, AR for lithium, is 6.9. You should be getting there for that. Okay, very good. Now, one last thing I need to bring to your attention, a more modern version of that question, and there is no such thing as more modern, it's just different ways of asking the same question, and you must be alert to that all the time, is that they would give you readings from the recorder of a mass spectrometer. And you need to be careful with that, okay? Now, there you are. It's 2018, and it's question 5. And I wonder how you're fixed with that. I'm going back on it again now. Define mass number of an atom. You're asked to define that number. That's the number of protons and neutrons in the nucleus of that atom. And then you're asked to define the relative atomic mass of the element. I'm going to leave that with you now. I hope you realize what you're being asked. This is the average mass, taking their isotopes into account, acknowledging their abundance, and on a specified scale. Now, please, any one of those 4 points missing and you lose serious marks there, okay? Next, a sample of magnesium metal was introduced into a mass spectrometer and vaporized. What were the next 3 fundamental processes that occur in a mass spectrometer? Now, folks, I am working on the premise that you've this done already, okay? People have mnemonics for these. I won't go there, but you need to remember the sequence. What's a mnemonic? It's a little rhyme that you make up when there is no logical order to what you're trying to remember. And it would be helpful if you would have something like that, okay? Vaporization, ionization, acceleration, separation, and detection are the 5 stages. They have asked us there, what are the next 3 fundamentals? They gave you introduction, okay, into a mass spectrometer and vaporized. So the sample was vaporized and they want the next 3 stages. There they are, ionization, acceleration, and separation. Now, that's a subset within that, but it will be done under the heading of instrumentation. I'm hoping many of you are saying to me, I know that already. And if that's the case, that would be very good. Now, let's finish this unit as follows, right? As follows. The mass spectrum of a sample given below shows that magnesium has 3 naturally occurring isotopes. Now, I hope you can read this, but it says mass number here. Now, everybody should make a note of every exam question I refer to. 2018 question 5, I'm on part C. This is the mass number of the isotope, and this is the abundance. Unless there's any ambiguity with the scale, they've written the percentages over each of the lines. Now, that's exactly how it would come out on the mass spectrometer. On a little recorder or a screen, there'd be peaks on it. And each peak would represent a certain percentage. And that's what you have here, nothing more than that. So there's 79% of an isotope of mass 24. And they did say magnesium. So there you go. Magnesium 24 has a percentage of 79%. The next isotope is magnesium 25. And it has a percentage of 10%. And the last one is magnesium 26, magnesium 26, and it has a percentage of 11%. It would be a great help if those three numbers added up to 100. Good. Now please, take 79 atoms and multiply by its mass. Take 10 atoms and multiply by its mass. Take 11 atoms and multiply by its mass. Add the three numbers together and you'll get the total mass of 100 atoms, and divide by 100 and you'll get the mass of 1. And the answer you should get is 24.32. Now you need to try that, and you need to do it please with a calculator. Take your time and you should be getting all the marks for that. Use the data, it says here, use the data to calculate the relative atomic mass of magnesium, correct to 2 decimal places. Okay, now please be careful, won't you, when you're doing that, because that's an easy question in the sense you have great control over the content there. And as I finish this unit now, I just want to say to you, will you all please be aware that you don't learn definitions. There's a concept behind them. Grapple with the concept, get the idea clear, and then you'll articulate it much better. Now, that's the end of this unit, okay?